In this video, we're going to be exploring a very simple machine learning project that helps to recommend crop type for farmers to be able to know what is the suitable crop to plant based on the soil and the climate of their cropland. So this project is based on a dataset from Kaggle, where we have the crop recommendation dataset and we have the information about the dataset. So before we go further, my name is Meshak, and I'm a data scientist applying machine learning in agriculture and environment. If you're watching this video and you like it, feel free to click the like button and also subscribe so you can get notified quickly and easily whenever I upload a new video. So let's move on. So this data set of crop recommendation, we have the ratio of nitrogen content in the soil, the phosphorus content in the soil, potassium content in the soil. We have the temperature, we have humidity, we have pH, and we have rainfall. This is what we have about the data set, and we can go ahead to download it. Normally, you can download it as a zip file, but here I'll be downloading it using the code, the Kaggle library. So we're going to be using Google Colab for our programming and whatever we want to do. Google Colab is a Jupyter Notebook service offered by Google that allows us to run our Python code. You can run your R code, you can use GPU, you can use CPU, and you can just benefit a lot from it. So we'll move on into the project I want to do. The first thing I'm going to do is to just upload the library that I want to use for this project. And here we're using pandas, numpy, matplotlib, and we're using seedborn. Seedborn is and matplotlib, they are for visualization, and numpy is for mathematical operation, and pandas is to handle our data sets and to manipulate it the right way. So if you want to learn more about pandas, I have a video that's linked here where you can watch my introduction to pandas and introduction to data science at large. So let's run the code. And this is connecting to the server. And this will take just 3 seconds. Now it's done. Then we can move to the next thing. The next thing we want to do is we need the data. And we're going to be using Kaggle, whatever we have right here. We'll just copy this as is. I can just click copy code and I'll come to the cell and say download latest version, and I'll just run that. So this will run and it will return the path to the data set that I need to use. So using the path, that is what I will be using to get my crop data set. But another thing that I need to do is I want to know what are the files that we have in this path. So to do that, I will run a terminal command using this exclamation mark and say ls, which is the list, and I'm going to copy the path. And that is going to tell me what file is inside the path. You see, we have crop recommendation CSV. So the data we need is inside that path. Now we just need to be able to link to it using our code. So let me cancel this part. Then we just say our data frame for pandas, you say pandas pd.read CSV because we've imported pandas as pd already. So we just say pd.read CSV. And I will just copy the directory that we have. So this is the directory. I'll pass it in and I'll just say slash and I'll copy the name of the file and put it there. So this should be able to load the data that we need. So let's check the data. Just view it and say df.head. So you can see now we have the data set, just like what they gave in instruction in the data context and for the data fields. So we have all these variables and we have now all the variables, and the label, we have it as the crops. These are the crops. So based on the soil properties and climate properties, we can then predict if rice is suitable for such an area or not. So we'll find that out as we go. Then we just need to check all the crops that we have. And to do that, we just say df and we call the label, which is this, and pass it and say df label, and we want to see just the unique. We want to see all the crops that we have. So we have unique and yes, so these are the crops we have, and we can see how many are the crops. So usually I can easily just say length, len, and I can copy this whole thing into it because it is now a list, so I can easily check the length. So we have 22 of them. We have about 22 of them. So that is nice. We can move on to the next thing that we need to do, which is to just say df.info, which is to see what are the other things that I need to know about the data. So now we're exploring the data. So I'll say df.info, and that will give me some information that I need to know about the data. So here, df.info is helping me to understand that we don't have any missing value. That is non-null. So there's no null value in my data set. So that is why I have everything complete. So we have 2,200 rows in my data set, and each variable has a value for each row. So, and that is very important. Then another thing we can do to see our data better is to do df.describe. So I can say df, which is our data frame, dot describe, to just describe the data. So now the data has been described. But one of the things you will notice in our data when I use df.describe is that df.describe focuses on the numeric values. So here we can see our label in df.info, but we're not seeing our label here. It's because it focuses on the numeric value to calculate the statistics. So we can't easily calculate the statistics for string value or string variable. So here we have for the nitrogen, we have the maximum as 140. We have the minimum, of course, as 0. There's some places where they have 0. We have the standard deviation. We have the mean. And the same for others. So when you look at this, it will help you to understand, okay, what are the ranges of my value that I want to use for my modeling process. Now, another thing that is nice to look at is the data type. So here we have the data type as integer and float, and the label is an object. So it's also good to look at it. But if you want to see the data type clearly for yourself, you can just say df.dtypes and just run that, and you can see you have df.dtypes, so it will tell you directly. So the same information you have here, you can see the same information right here. So that's how you do that. Okay. When we are having like a classification problem that we're dealing with, because this is a classification problem, if you don't understand what I'm saying clearly, there's a video that is linked here where I explain different kind of machine learning problems, where I categorize the different learning style from supervised to unsupervised to semi-supervised. So if you watch the video, it will be clear. But here, I'll just focus on the project. So for each of the class that we are predicting, we want to see how many are they within the data set, because it is very important to know that, because if we don't know it, and let's say for rice, we only have 10 rows containing rice in the old data set, it will introduce some kind of biasness in how our model is learning because there's data imbalance. So to check that, we're just going to do df and say df label, and we're going to check the value count, and run that. Then you see, so luckily for us, this data is very clean. It doesn't completely mimic how reward data look like, but yeah, it works. So we have the rice, we have 100 of each of the crop that we're going to be predicting, and that is kind of nice. So there's no data imbalance. So we can move on to the next thing that we need to do. Now, the next thing we want to do is we want to check how the crops interact with different soil and environmental variable. That is what we want to check right now. So we want to see how do they interact with the nitrogen, the phosphorus, the potassium, and all other. And to do that, I have like a code written here that makes it easy. So this notebook will be available, and you can download it or access it using the link that is attached to this video, and you can just follow the process. So I have this code to make the plot, so everything could be quick, and I will explain what this is doing. So the first thing here is we need to capture the numeric columns and drop the label, that is the object, use a string column. That is not what we want to explore. So by doing this df column to drop label, now we have the name of the names of the columns that are just numeric, and that here we are checking the length of the column. And to divide just our figure to get the number of rows that our figure should have, it is the number of columns plus 1, and we are dividing it by 2, ensuring that it's divisible by 2. Then here, this is plotting the figure into subplot, because we want to have multiple plots. And this is a for loop that is looping through the data and plotting each variable separately. And the last part of the code, which is this for loop, is helping us so that if we have the count of our data. So to make it clear, I think, let me remove this part and just make the plot. So I'll run it so you can see the plot. Okay, now, if you look at the plot, so we have the average end value for each crop. So you can see here for apple, this is the average end value. For banana, this is the average nitrogen value and all. Then same as phosphorus and potassium and temperature and all others. But if you look at this plot, you see that we have this part that is nothing, but it is empty. That's because the subplot, for it to be balanced, it is ensuring that all the plotting space that is required is within the whole figure. But since we don't need this, our variable ends at rainfall. So to remove that, that is what this for loop is doing. So that is all we are doing. So we are deleting it. We are deleting the axis. So you can see. So if I run this again and we check, you will see that now the place is just empty. So our plot is neat and it makes sense. So this is just to see those interactions, so we can see the way when we have apple, what is the average rainfall value in a place where you can grow apple, what is the average rainfall value in a place where you can grow banana, and you can look into this scientifically and begin to understand things better. So we'll move now into doing some correlation. In machine learning project, it is very important to see what variables are correlated with each other, because sometimes if you have a lot of variables or a lot of columns, to demystify it, you may need to drop some if they are very correlated, because if they are correlated, they are not really introducing new information into the data. So, but we can do the correlation plot. I'll also bring the code to plot the correlation that has been pre-written here. And to do the correlation, we can see here correlation matrix. And when I run the correlation matrix, you will see the matrix here. One of the things you will notice is based on the color, of course, the color, the closer to the red, it means they are highly correlated. And when they are closer to the blue part down here, it means they are not very correlated. But something stands out when you look at the correlation plot. So you see that there's a kind of interaction between the phosphorus and the potassium. So there's an interesting relationship between potassium and the phosphorus. So you can see they are very correlated. Also, yeah, that's the main thing. So we can see how that they are very much correlated. But because here, it is not simply correlation is complete, like 1. So I will still retain it in my data. I won't be dropping them. So that introduces something that is very important. To move to the next part, we will check the data distribution. So to check the distribution, because we're going to be checking the distribution multiple times, I have created a function that will allow us to check it easily right here. So this is the function. So every time we run plot underscore dist, we'll be able to see the plot that we need. So I'll just run that, and I'll just run the code to plot the distribution. So I'll just plot dist, open bracket, then we pass in our data frame, the df that we'll be using. Then I'll pass df there, and it will make the plot for us. So if you look at it now, you'll see that this looks like it is skewed towards the right, and you just see the distribution of the data. Every of the data set, only pH and temperature, they look a bit like they follow a normal distribution. Of course, not perfectly normal. If you look at it, you will see that it is symmetrical. And if you look at the other one too, you see that this is also symmetrical compared to the other one. So here you will see that we are having like different distribution. So this is like one distribution around this area, another one here, and another one here. So this may affect how the model is learning, but there's something we can do about it if our data does not follow a specific a normal distribution. So we can scale the data. That is what we do. You can scale the data, and there are different ways you can scale the data. You can do minimum, maximum scaling, min-max scaling. You can do standard scaling. You can do log scaling. There's Joule-Johnson's transformation that you can do, and there are lots of them that you can do to your data. But in this case, I'm going to be using a standard scaler. And to use the standard scaler, I'm going to be importing the standard scaler from sklearn Dutch preprocessing. So this is it. And I will initialize the standard scaler. And I'm going to create a new data frame from that, because I don't want it to alter the initial data frame. And I will say df scaled, and I'll say scalar, which is what I've initialized here. I'll just say does fit transform, because I want to transform the data. I'll say scalar does fit transform. Okay, what is wrong here? Okay, scalar. Okay, that's df scaled equals scalar dot fit transform. And what we want to transform, we're not transforming the label, so we need to drop it while we're doing it. So we say df dot drop, and we pass in the column that we want to drop, and we introduce, okay, what is the axis of the column? Our label is in the column. Of course, if the column, so it's going to be in axis number 1. If it's a row, it's going to be in axis number 0. So we say axis equals 1, and from here we can drop the data and then convert it back to data frame. I prefer that because it helps me to be able to visualize the data better. So to do the conversion to data frame, I'll just say df underscore scaled, and I'll say equals to pd dot data frame df underscore scaled, and pass in the columns that I want to drop. So to make it easy for myself, I'll just say pass in the columns that I want to drop, just like what we have already initially. Then I'll just pass it here. So this is the column to drop. So now we have that. So if we check our df scaled, you will see that the values will be different compared to what it used to be in the df. So you can see now you have some minus value. It is the scaling that is affecting that. Now that we've scaled it, we want to check the distribution if there's any change from that. So I will just say plot this using the same function that we had before. I'll just say df scaled and run that just to see. And initially this was normal, this is still normal, but it is not making any difference. If I look at it, it is not making any difference. This is skewed, it is still remaining the same, just like what it used to be. So the standard scaling is not making so much difference. So I'll do another kind of scaling here. I'm going to do log scaling. I'll just try to use logarithm to scale it, and I'll copy the code for the log scaling and see if the log scaling will make any difference. Now I have it, and I'll just say plot dist and say df log as the data frame and just plot it and see the difference. So this still follows the way it used to be. This seems better, but not very much. This now looks like it's showing differently compared to what it used to be, but I still don't think it's making so much difference in the end based on the way I view it. So here I'm only confident about the normal distribution of temperature and pH. So based on that, I'm just going to ignore the scaling completely. I don't think it's making any big difference, so I'll use my data set as is. So to do that, I will move into the modeling phase. I'll just continue the model training. So let me call this modeling. And yep, so this is the modeling. And to model, I will import all the libraries that I need. So here I'm using train test split, and train test split is what we can use to split our data set from between training and testing. Then we have the label encoder. The label encoder is very much required because the models we use don't really understand the string characters. They understand numbers. So we need to encode our label. For example, instead of having rice, let me go up. So instead of having rice or apple, we have it as maybe 0 and banana as 1 and black gram as 2 and also. So that is what we're going to have. That's why we have the label encoder. That's what it does. Now, logistic regression is a model, a classification model that we're going to be using. I spoke about it briefly in the video on the introduction to machine learning or machine learning foundation. And here we have the decision tree classifier, the random forest classifier, gradient boosting classifier. Then we have a support vector classifier. And we have XGBoost, the extreme gradient boosting. So we're going to be trying about how many models here? This is 1, 2, 3, 4, 5, 6. So we're going to be testing 6 models and see how they can help us predict which crop is suitable for a specific soil and climate. So we'll move to the next thing, which is the label encoding. And for the label encoding, I have the code, and I will just walk you through what we are doing with the label encoding. Now, this is the label encoder. So we initialize it or instantiate it. This is label encoder, and here we instantiate it, so it's here, and we can use it from there. Then we have our label, and we're just updating our label with the transformed label. So label encoder.fit transform. Then we have our X, which is to drop the label. Our X is going to be input that we're using to train the model, and the Y is going to be the label. So we are sending the label there. And here we are doing our train test split because we want to split our data into training set, validation set, and test set. So the training set is what we do first. So we have the training and the test set. And the training and test set, we get that from the X and the Y. So we have the training and test set, and we are just saying we want the test set to be 10% of the data. So that's the test size, that's 0.1. So we want to take 10% of the data out and use that for our testing. And stratify equals Y is because we have classification problem. And in classification problem, if I don't use this stratify, if I don't stratify the label, there's a high chance that in a part of the data set, you might have rice in a part of the data set and you don't have rice in the test data set. If I don't stratify, you may have some crops in the training data and you don't have those crops in the validation data. So it is very important to do this when working with classification problem. In regression problem, I don't necessarily need it. So to get our X train now, we now take the training data and get our training and validation data, which is the XCV. And from the total length of the training data, this X training, we want to take 0.2 from the training data, which is 20% as the validation data, and the 80% of that total training data, we have it for the training, and we just run that. Now to see if our label encoder is working correctly, I think we can check if our label encoder encoded things accurately. So I will just say for I, then crop in enumerates, and I'll say label encoder dot classes. So this is a part of the label encoder method. So when you check the documentation, you will see it better. And I will say print I and crop. So what I'm saying here is I want to see what is the index. That is what is the label that was attached to it, the code that was attached to the label. then I want to see what crop and which code belongs to which. So when I do that, I'm print to, you can see 0 is apple, 1 is banana, 2 is black gram, and all. And we can prove that by just doing df.head to C. Okay, so you can see now. So instead of rice, we now have 20 as the label. So that is great. For us to do the model training, we now have our data set, we have the training data set, we have the test data set, we have the validation data set. So in the training phase, we're going to be using our training and validation set for the training process. Then we're going to be testing after we have our final model. Now that we have the training and the test set, and we have also the validation set, we need to instantiate all the models that we want to use. And I'll just copy the code that we have already here, and I'll explain it. So you can see for logistic regression, we have the max iteration, and we have the solver. And the importance of the solver in this logistic regression is so that the model will not stop training until it has converged successfully. So that is what the solver is for. If I don't use the solver, you will get a warning. So I'm just using Saga as the solver here to help the model converge correctly. Now, decision tree, we just had a random state, random forest classifier, the hyperparameter, we just say n estimator equals 100, but we can do hyperparameter tuning. In future video, I'm going to be talking about hyperparameter tuning, and we're going to see how do we tune the parameters of our model to get better performance. And we have the gradient boosting classifier, which is the random state 42. Then the support vector classifier, we just pass in the random state. We don't want to work with a lot of parameters because for each of these models, there are different parameters that we can tweak. But here, I'm just trying to simplify them as much as possible. So I'll just run that. Then I want to create a dictionary that we have all my model names that I need because I want to refer to the model name and the model at some point. So here I have the dictionary, and in this dictionary, I have logistic regression, which is the LR, decision tree. You can name this anything as you want, but here decision tree DT, just to make it clear. So I have the name and I have the model assigned. So I'll just say models. And here now we want to train the model in a loop. So I have the for loop to train the model. So the key in the dictionary is the model name, and the value is the model, that is the LR. So for the name and the model in model.items, which because it's a dictionary, now we are fitting the X train and the Y train using that specific model, and we are going to make prediction and check the accuracy, both the validation accuracy and the training accuracy. And here, validation accuracy is using the validation set to check, that is the X and the Y for the validation. And training accuracy is using the training data itself to check if the model learned itself, the data given correctly. So when I run that, we just wait a bit to see. Okay, the training, and that will take a few seconds because there's not a lot of data. Now we have the accuracy, and we have for the logistic regression, we have the decision tree, random forest, gradient boosting. But from all I see here, I could see that the random forest seems to have the highest accuracy among them with respect to the validation accuracy compared to all others. And the closest one to that is the XGBoost, the extreme gradient boosting. And the decision tree also is closer to it. So based on the judgment, based on the accuracy, I will select the random forest as the final model that I'm going to be fitting and be using for the last phase of what I want to do in the model training. So to do that, I will calculate other metrics just to be sure that my model is performing well. So I have the random forest model here, and I'm going to be using RF as the final model. So to calculate other metrics, I'll bring the code in and go line by line or chunk by chunk to explain what you're doing. So this is going to be calculating the metrics. We have the accuracy, the confusion matrix. We know the accuracy already, but we're going to be calculating everything together here and be fitting the model again. The way to explain that is the accuracy is the fraction of correct prediction, while you have the precision is the fraction of the positive prediction that are correct. So for each of the class, the precision checks how precise is the model predicting that specific class, and the recall is the fraction of actual positives correctly found. The actual positives correctly found. So that will help us minimize false negatives in the kind of prediction that we're doing. So in our case, if we look at the accuracy here, the cross-validation accuracy, which is the accuracy score, we indicate the correct crop prediction. The correct crop prediction across all the 22 classes of crops that we're predicting, while the precision is focused on what is the macro average mean. That is the macro average of the predicted crop. So if it looks at individual crop, the 22 crops, and it checks in each of them in how precise the model is able to predict them, what will then be the overall score of how correct they were predicted. Then the recall, it captures what is the true crop instance on average to minimize the missed identification of the crop. But we're going to see that clearly when we run the code. And that is going to, now you can see we have our confusion matrix. And our confusion matrix here, you can see in each of what we are predicting, we have 18 crops in class 0. And as you remember, in class 0 is apple. So we have in our validation data, we have 18 of them. And if you look at them, that there's nothing being mispredicted here. And when you look at all of them, all true, for our random forest classifier, it is not predicting anything wrongly because I can't see anywhere. Oh, except here, I could see in number 20. So there's a place where we have one crop mispredicted. So that is the only wrong prediction that we have. That is why we look at our precision, we're about 99% precise. The recall is also about 99%, and the F1 score is about 99%, where the F1 score is like the balance score, where it looks at the harmonic mean balancing of the precision and the recall. That is why if you want the formula to calculate the F1, this is how it is calculated, the F1 score mathematically. So if you look, this is the formula. You can see it is 2 multiplied by the precision multiplied by recall divided by precision plus recall. So I'll just clear that because that's not our focus. So basically here, we can see that our model is performing in a good way. You can see that our model is performing in a good way. So to pack the model in a way that is compact, in a way that is meaningful, we're going to be saving the model using a pipeline. And that's what we're going to be using to make it easy so that we can reuse the model later. So I will bring out the pipeline that we're going to be using here. So we have our pipeline here. Now we use Pico to pack our data. It helps us to be able to modularize our data, and we can import it elsewhere and use it for prediction later. Now we have the class, and in this class, we say the full pipeline with decoder. And why this is important is because we may need to use our model maybe for a web application or for other purposes. So doing this helps a lot in having a model that can be used in a good way. So to explain this code, the first one is the class itself, which is the class name that we have, and the def init. What we are doing here basically is we are constructing the method. So it is a constructor method that the setup runs when you create an instance of the class. So here in the constructor, we want to have the model as an input. I want to have the label encoder. And why the constructor is very important is that it makes the model and the label encoder available anywhere you want to use it within the class itself. So then the next thing here, we have the predict function. So we call it method. So it's a method of the class, the predict, and it defines how the prediction is made. So if you call the predict, what is happening here is that we're calling it the y predicted encoded. So we're getting the encoded value, but what we want to return is the inverse encoded. So what we want to get here when you run the prediction is going to tell you what specific crop was predicted, but it won't tell you the name of the crop. It will only tell you the code name that was given. So if it is apple, you're going to have 0 stored in the encoded. And what we are returning here is we're applying the label encoder and say inverse transform. That is from 0, show me that it is apple. Show me the text itself. And the predict encoder, this one is if you just want to predict the value itself, not the string. If you just want to get 1 or you want to get 2, the predict probability is you want to see this. How did the model make a decision of if that thing is apple or if it is rice or if it's any other kind of crop? And we can see that. And here you can save the model and use it later. So, but I don't really need to save the model right now. So I will remove this from the code. That is not what I need right now. So I'll just run this and we can then test. And this is where I'm instantiating the class. The full pipeline equals full pipeline with decoder. And we pass in the final model, which is what we have. Here we have the final model, which is the final random forest model, and we have the label encoder, which we created while we were trying to do the modeling process here. So we have the encoder that has been created. So we pass the two as variables into the class as properties of the class, and we can then run our prediction from there. So to make the prediction, we're going to be predicting on our test data, not our validation data, not our training data. We'll be predicting on our test data. That is, that data has not been seen by our model before. So we just say full pipeline dot predict. And we're going to see the difference now. Dot predict. And here we're predicting X tests, but I don't want to predict everything. I was x dot ilog and just say I want to just predict the first 10 in the test data set. The first 10, then I will run it and see what output I get. So you can see the first 10. So using the predict function already converted the code back to the crop name. So if I want to say, let me use the predict encoded so you can see the difference. So for the predict encoded method, I'll use predict encoded method and I'll run it. I see it only gave me the number. So you can see 6 is cotton, this is pigeon peas, 18, and coffee, and all others. Then if I want to see the probability, I can use the predict probability. So for the probability, I'm going to be using this line of code and be adjusting it to fit into it. So here I'm going to be having the probability method, predict probability, and I will have that here, and I'll just do it for 1 first. So when I run it, you see, so for every time you run the prediction, it's a probability that is being predicted. Then the final predicted value is the one with the highest probability. So the crop with the highest probability will be the right crop. So that is exactly how it works. So here you can see that the value on index 6 is the highest probability. So that is why 6 was returned, and 6 is the code for cotton, for example. Then pigeon pea, which is number 18, which is the second crop. So if I increase this to 2, or if I just say 1 to 2 instead, because I want to see the pigeon pea. So you can see here now, this is number 18. Here is on index 18, and that is why we have the pigeon pea right here. Now, because of this probability, if you sum all the values here together, you are going to have it equal to 1. So 0.97 plus 0.02 plus 0.01 will give you 1. So that is how it works. So we need to confirm that whatever we are predicting in our test is the same as what we have in our Y test. So we want to compare our predicted Y with our Y test to see if we're going to be getting the same prediction. So to do that, I will bring out the Y test. I'll just call this Y test because we have the Y test already saved. But I will call this Y test transformed because I want to have it in the prediction, the string value. So I'll say Y test transform because label encoder, just like what we had here, just like the same thing we have here. I'll just say label encoder dot inverse transform, label encoder dot inverse transform, and I will have Y test there, and I can then run that. So I have my Y test transform. I'll just say print Y test transform. Okay, I can just copy it and just say Y test transform. I want to get the first 10 also, and I'll say the first 10 and check if our output will be the same. So cotton, correct. Pigeon peas, correct. Coffee, correct. Maize. Here we can see that our prediction went wrong here. So instead of maize, instead of black gram, it predicted maize. So the prediction was wrong there. Then kidney beans predicted correctly. Then coconuts, banana, black gram, chickpea, and pigeon peas. So that right there is our final model. So that's how we do the crop type classification based on the soil and climate property. I believe you've learned something, and if this has really benefited you, feel free to like the video and also subscribe so that the algorithm can push this video to other people that need to learn from it. So thank you very much.